So now I think it's right time to go, just to get a feeling of what we already did now. Let's try to take an example to determine the element stiffness matrix, or how the evolution of the element stiffness matrix can be explained using an example of an LST element. So let's write down, let's say, so this point 6.1, let's call it all the derivation related equations. And in the 6.2, let's focus on an example of a linear strain triangular element. Example of how the stiffness could be determined using the mechanical properties as well as the geometric properties. So in order to, let's say, start or to get a grasp of what we already did, which we quickly glanced now in the previous hour, let's try to look at a LST element having specific coordinate system or specific, let's say, nodes, having a triangle of base D having a dimension B and a height H for the particular problem that we're tackling now. Okay, we have the coordinate system. Use another color. The X and the Y coordinate system. We have 6 nodes. We can introduce 6 nodes, 3 nodes, 3 n nodes, and the other 3 are located in the middle. So we know the triangle which we consider has a base dimension, base having a dimension of D and a height of H. So using this, we can write down the nodal coordinates of each node. So let's take the origin at node number 1, which corresponds to 0, 0. So node number 2, since our base has a dimension B, it's B0. Node number 3 has a height of H, so it's 0H. Node 6 is the mid-side node of the base, so it's B divided by 2 times 0, 2, 0. And the mid-side node of the vertical edge has 0 by 2, the coordinate system. Node 4 has this coordinate system, the coordinates to define the LST element. So now it would be good if you can, like, if you're not already taking down notes with me, it's good to take out a piece of paper and work out this problem with me, so that you will, the things will be more clear to you rather than staring at the screen, which might, where you might lose your attention. So it's, let's try to move on. So what we do in the first place is we calculate the coefficients A1 to A6 by using equation 6.1.5, that is to describe the displacement at each coordinates, that is to describe U1, the displacements in the X direction and the displacements in the Y direction. Okay, this is what we are trying to do. Okay, so since we already know the nodal coordinates of each of the system, what we can do is we using equation, let me write, using equation 6.1.5, which is nothing but this 6.1.5. Since we already know the nodal coordinate system, we are interested in calculating u1 up to v6 uh, and by substituting the corresponding nodal coordinates. So here in this case, in this equation, you can see we have substituted x1, y1. So similarly, we will be substituting the corresponding nodal coordinates and expressing in terms of the coefficients. So the first step, finding the writing down the displacements of the coordinates using the nodal coordinates from u1 to u6. So u1 is, the coordinate is 0, 0, 0. So if we substitute 0 and 0, what you would end up is getting only a1. And the second node, the x displacement function, the corresponding nodal coordinates are b, 0. The function you would get is a2 times b times a4 b squared. Similarly, for u3, the displacement in the x direction is a function of the nodal coordinates given by 0, h. And when you substitute it in the shape function, displacement function, the corresponding x terms would be 0 and the y terms and the constant term will be standing or remaining. So for u4, you would get a function which contains both x and y coordinates, since none of them are 0. Just please correct me if I make a mistake here. A3 times h2 by 2, and a4 is a multiplication of a4 is x squared, that is b divided by 2 squared. A5 term is a x and y term, so it's b h divided by 4, and a6 is a y squared term, that is h by 2 squared. So similarly, you can write u5. So with the nodal coordinates are 0, h by 2 is a1, a3, h by 2, and the last term would be the y term remaining, a6, that is h2 squared. So u6, similarly, here the x term is the constant value, but the y term is missing, and the corresponding constant terms as well as the x terms will be present, whereas all the y terms will vanish, a4, and the squared term b2 divided by 2 squared. So we have written down all the displacement functions, displacement at the x displacements at all the 6 nodes, and based on the 6 equations, we can find or solve for a values in order to obtain, let's call it, the equations. By solving equations 6.2.1, we were able to express now the constant terms. We can obtain the ai terms, and the corresponding ai terms would be A1 would be U1. If you do, if you can do it on your own and check whether you get the correct answers. 4 times U6 B. A3 is 4 times U5, 3U1 minus U3 H. Similarly, you can write A4. You can try on your own and write A4, A5, and A6 to obtain the required answers for, let's say, A1 to A6. So this is equation 6.2.2. Okay. So once you have the values for the corresponding coefficients from A1 to A6, now you can substitute them in equation the first equation, that is 6.1.2, that is you can obtain the values from A1 to A6 and substitute them in equation, let me show you. In this equation, yeah. So what you have done is you have found all the corresponding A1s, A values for A's. Since you have already found the values for these coefficients as a function of U, you can substitute these the values which you have obtained in this equation and also apply the of course in this equation to obtain an expression for U, since you already found the A1 to A6 coefficients. So similarly, you can do the same procedure again for V, apply the Cartesian coordinate systems or the nodal coordinates corresponding to each node, and write down a simultaneous set of equations for V1 to V6 and solve this simultaneous set of equations to obtain the coefficients from A7 to A12, and also substitute the corresponding values in equation 6. To explain these equations, the displacement in V direction. So I will skip these steps. You can try it on your own, and if there are any questions, you can ask me. So what you would do is, now since you have already found A1 to A6, you can substitute these equations from A1 to A6, substitute the values which you got from A2 to A2, 6.222 AI values into equation 6.1.2. What you would get is, so you can try it on your own to get the coefficients from A4 to A6. I will write down the complete displacement function in the y direction. What you would get is U1 and for, let's say, A1, and the next term would be just let me know if I made a mistake. You can try it on your own, and if I made a mistake, just let me know. U5, 3U1. You can try this on your own. So I'm writing down because I already skipped the previous step, so that now you can verify whether you have done the arithmetic correctly, the math correctly, so that you would end up in getting the correct answer. So you can verify your results by comparing with this set of equations. All right. the xy term, and all right. So now you have obtained a equation, the displacement function in the x direction, and as the next step, of course, you can do the same procedure to obtain a displacement function in the v direction or in the y direction. So following the same procedure that we just described, write down the equations from v1 to v6, apply the nodal coordinates, solve the set of simultaneous equations to find the coefficients from a6, a7 to a12, and then back substitute in the initial equation to obtain the displacement function for v. So now you have u and v. What do we do in the next step is we try to simply separate it to, let's say, the expression of a displacement function. This is what we already did in the previous cases also. Since we have a function for u and v, then we would like to express now this in terms of a shape function, because u and v correspond to, let's say, nodal degrees of freedom. We already know that. So u6 and v6. So we would like to describe this in terms of shape functions. For this, we slightly rearrange the equations. So let me write it like this. So this is, let's say, a matrix. It's a 2 by 12 matrix, which describes the shape function. So what we do is, how the shape functions are obtained is by simply collecting the coefficients, and by multiplying, let's say, before that I will write down the shape function so that it will be clear. In order to define the shape function, what we do is n1 0 So likewise, you would have terms until n6. So this is nothing but you have simply rearranged this equation to find out, to define certain shape functions. Okay, let's go this. Six point 2.5, just to be consistent with the, let's say, reference which I will be posting later onwards. So I have skipped the equation which we will obtain for the displacement in the y direction, that is v. So if you rearrange these equations, you would get the displacements as from n1 to, let's say, n6. I think it's maybe I can skip all these steps, and maybe you can solve it out on your own to see what you get. I will only write down, let's say, if you separate, what we do is we collect all the coefficients of the shape functions and then multiply each by the corresponding ui term. So for example, if we collect all the terms and multiply it by u1, then we obtain capital N1 value. So these shape functions can be resolved using by this method. And I will only write down, let's say, the shape function of, if you N6 would be, of course, just to show you that's a function of x and y, which describes the displacement within the element. Yeah. So similarly, you can obtain from N1 to N5 the other shape functions. So now we have obtained the shape functions. So using these shape functions, we can, and by performing, let's say, the differentiation indicated in the previous section, that is, let me show you this, the differentiation for obtaining the strain. We know the strain, yeah, for the strain within the element, for obtaining the strain within the element, we have to perform differentiation with respect to x, y, as well as in order to take the rotation, we have to get the combination of these two differential terms. So now, since we have obtained expressions for u and v in terms of shape functions, we can perform the differentiation and obtain the corresponding strain matrix. So the strain is nothing but the B matrix times the D matrix, and the terms of the B matrix, you can recollect, there are like beta terms and gamma terms, which are functions of coordinate system. These beta 1 and gamma terms can be calculated. These terms, so this beta and gamma terms, can be calculated. So these are functions of nodal coordinates, calculated by solving this equation. So if you do the correctly, I will write down, let's say, only the components. I will not write down the B matrix, but I will write down the corresponding beta terms and gamma terms, so that you can work it out on your own and see whether you get the correct results. Okay, so you would get beta 1 to be minus 3h 4x b plus 4y beta 2 term as 4hx plus b. So the important thing is that you do it on your own and check whether you get the correct answers, and clarify with me if there are any doubts. The motivation behind, let's say, of this section is, as you can see, this is quite lengthy equations that you need to apply, let's say, different mathematical principles in order to solve this. So it's better done with the computer rather than performing longhand calculations. But no matter how the element gets complicated, the procedure is same for all the types of elements. This is what I want to motivate you. So 3b, the gamma terms now, they are again functions of x and y. Gamma 2 is 0. And I'm presenting this information just for the sake of completeness of the section. All right, for x. So long equations. And once you find these beta and gamma values, and what you can do is you can use these values to find the strains by substituting the B matrix and using the corresponding D matrix. to obtain the values for the corresponding strains of the different, let's say, of the within this element. So if you substitute this in the equation 6.2.7, what you would get is the strain in the x direction would be also a function of, let's say, the area and beta 1 u1 strain in bidirection is 1 over 2a gamma 1 v1 gamma 2 v2. These are functions of v now. Rotations in the xy plane. So now the stiffness matrix for a, let's say, thickness element can be obtained by substituting these equations for obtaining B, and of course performing, since we already have this matrix, B matrix, we can, after obtaining the B matrix, since we already have the strain matrix and the D matrix, we can obtain the B matrix. And once we have this, what I wanted to show you, we can substitute this all this B matrix and the constitutive matrix into this equation, to this, however, there are so many equations that I have already trying to miss out all this. Yeah, this substitute into this equation, the fundamental equation, and perform the integration. Once you have the B matrix, you can find the transpose and multiply also with the constitutive matrix and perform the triple integral using a computer in order to calculate the element stiffness matrix for the linear strain triangular element. Yeah, so we already see now for higher order elements, and when the number of degrees of freedom increases, and when the order of the polynomial, order of the shape functions increases, this process becomes quite cumbersome, and you exactly need help of a computer to solve this, solve such problems. There are a lot of equations, and I skipped a lot of steps because we already went through it in deriving the CST element. I will provide some additional material. You can, and I have also used the corresponding, let's say, references or the equations, so that you will be easy. It will be convenient for you to follow, let's say, the supporting material, which I will be uploading. Just try to follow the steps and work out the math on your own, so you get the hang of it. Okay. So on that note, let's finish the section on the constant strain and the linear strain triangular elements. And in the lab classes, you already have applied, tackled some problems, and I hope it was interesting for you all, and hope you will be using this throughout your undergraduate period, as well as when you perform your duties as an engineer. And just before we move on to the next section, that is more focus on the isometric parameter formulations, which is also again quite useful method for the when we talk or when we solve problems in connection with the software, software simulations, or more specifically when we deal with different degrees of freedom or let's say different coordinates axis. uh, I thought of discussing some important considerations which might be helpful for you to tackle um, some problems in modeling as well as interpreting results, especially when we talk about examples in connection with plane stress and plane strain analysis. So since again there are umpteen number of ways, there are so many points that we can consider, or we should consider when we are tackling a problem. And I cannot mention all these points within the short period of time. I will just mention some of the briefly mention some important points where you can do a bit of reading on your own, and depending on the problem, you can apply these different concepts um, to solve your problems effectively. As I mentioned before, this is a matter of experience. The more experienced you are, uh, you will be able to apply a vast amount of knowledge in order to refining your model or improving your finite element simulation results.